In this lesson, we will concentrate on the general performance principles of an aeroplane in the en route phase of flight. Performance in the en route phase can be measured using the aeroplane's range and endurance parameters. These will be discussed in detail later on in the lesson. Let us firstly examine the forces acting on an aircraft in the cruise. These forces are split into couples. The first of these couples is produced by lift and weight. Weight acts through the center of gravity of the aeroplane directly towards the center of the Earth. Lift balances weight and acts through the center of pressure shown here. The effect of this couple on the aeroplane is to cause a nose-down pitching moment. The lift-weight couple is comparatively strong and thus the nose-down pitching moment is large. As an example of the size of these forces, in a 737-800 series, the maximum structural mass is 79,000 kilograms. At this mass, the aeroplane weighs around 770,000 newtons. Obviously, this weight will be balanced in cruising flight by an equal and opposite lift force of 770,000 newtons. The second couple acting upon an aeroplane in flight is that produced by the forces of thrust and drag. The effect of this couple is to cause a nose-up pitching moment. Notice though that this couple is far weaker than the lift-weight couple. The maximum thrust produced by the engines of a 737-800 is only 214,000 newtons. This means that the nose-up pitching moment does not balance the stronger nose-down pitching moment of the lift-weight couple. As a result, there is still a nose-down tendency. In order to maintain level flight, we need somehow to generate an opposite moment which will balance the residual nose-down pitching tendency. This is achieved by the tailplane, or horizontal stabilizer, on the aeroplane's tail assembly. The horizontal stabilizer, or tailplane, must be set at an angle which will cause a nose-up pitching moment to balance the aeroplane, or, more commonly expressed, to trim the aeroplane. Notice that now the nose-up and nose-down pitching moments are in balance and level flight is possible. The downforce generated at the tail is called tailplane downforce or tail load. Although such a force is necessary for level flight, it does have two adverse effects on aircraft performance. Firstly, notice that the tailplane downforce acts in the same direction as weight. It therefore increases the effective weight of the aircraft. The second adverse effect of the tailplane downforce is its contribution to drag. The tailplane is an aerodynamic surface designed to produce lift. It will, therefore, produce induced drag as well as parasite drag. Therefore, the greater the amount of balancing force produced by the tailplane, the greater the aeroplane aerodynamic drag. We will shortly understand that the two additional forces provided by the tailplane are detrimental to the aeroplane's en route performance in terms of range and endurance. To some extent, the amount of tailplane downforce required for level flight can be manipulated by changing the center of gravity. In flight, this can be done in one of two ways. Firstly, by selective fuel consumption, or secondly, by fuel transfer. Consuming fuel in the tail first, or transferring fuel out of the tail to other tanks, will move the center of gravity position forwards. Conversely, using fuel in the center or forward tanks first, or transferring fuel out of these tanks will cause the center of gravity to move aft. If the center of gravity moves forwards, the magnitude of the lift-weight couple increases because the arm of the two forces is now longer. This increases the nose-down pitching moment. To balance the nose-down pitching moment and maintain level flight, more tailplane downforce is needed. You may recall that this had the effect of increasing the weight and drag of the aeroplane, which would have a detrimental effect on the aircraft's performance, reducing both its range and endurance. If the centre of gravity moves aft, the strength of the lift-weight couple is decreased because the arm of the two forces is now shorter. This decreases the nose-down pitching moment. To balance nose-down pitching moment, less tailplane downforce is needed to maintain level flight. Reducing tailplane downforce reduces drag and effective weight, which will increase both the aeroplane's range and endurance capability. Remember that, before you fly, when carrying out a weight and balance check, also ensure that the centre of gravity is still within the limits published in the aircraft manual. Be extra careful when handling data produced by countries whose units of measurement are different to those you are used to.